All right, so we're studying control volumes or applying control volumes to open systems, and the big theme for this chapter is the first law. First law of thermodynamics applied to many different systems that are modeled using open systems. So nozzles, diffusers, turbines, compressors, etc. Almost all of them are steady state. We will have a transient analysis for certain limited cases at the end of this chapter. We'll get to it. Last time we did emphasize conservation of mass before we moved into conservation of energy. I think it's easy to get the mass down before you get into energy. We're going to be talking about fluid that's displaced by a piston. And this is going to be the edge of a control volume right here. And what we're going to be doing is we're going to be looking at over a time period of interest, that the piston will have moved from this location to that location such that it's flush with the control volume boundary. And maybe this is some inlet pipe. The cross-sectional area of this piston would be related to the diameter of the pipe by pi d squared over 4. True? Pi d squared over 4. And if you knew the displacement, the movement from the face, the front face to the front face from location 1 to location 2, that would be a length of travel, delta x. Then you have the product of the cross-sectional area times the delta x would give you the volume swept. Something like that. True? The volume swept. That volume would have been pushed into the control volume. This is the control volume over here. This is the inlet pipe feeding it. Okay. Well, what would be the mass pushed in? The mass pushed in. How much, a little chunk of mass would be pushed into the control volume would be that volume swept in, A times delta x times the density, or the cross-sectional area times delta x times 1 over the specific volume. Hopefully all that, maybe the new way of putting these terms together, but it makes sense. Hopefully that makes sense to you. So if I'm interested, I could take this equation and divide by delta t, and I group it with that term, and I group it over here. And then what does that look like? That looks like a mass flow rate flowing in is equal to the area, cross-sectional area of the inlet pipe, pi d squared over 4, times some velocity, that's distance over time, some distance traveled. So it's the velocity of the face of the piston, which is the velocity of every little chunk of fluid in there being all moved to the right as shown. 1 over v. So what is AV? Volumetric flow rate. Volumetric flow rate divided by the specific volume gives you the mass flow rate. All right. Okay. One thing before I leave this slide, this is all setting up for mass and mass flow rate, but we're going to have to deal with boundary work. All right. Boundary work, the equation that you remember is something like integral P dV, right? Integral P dV. Well, think about a little bit of boundary work that maybe the piston's doing to push that fluid into the control volume. Okay, that would be the pressure times the area times the delta x. Isn't this a dV, the volume swept in? The volume, maybe I should have put a delta V for the volume swept inside, pushed in. And so if we say, okay, well, if I look at this term over here, I have an area. Let me see if I can write that a little better. Maybe write this equation right up here. Let's go ahead and write it. The mass that's swept in is equal to the cross-sectional area times that displacement, so this product A times delta X is that volume swept in, divided by the specific volume coming in. True? So this is also equal to P times V times how much mass was swept in. So it's that inlet pressure times the inlet specific volume times the amount of mass that's swept in. That's that boundary work. I know that equation's new, but can you see why I wanted to write it that way? I get a natural PV term. What is the definition of enthalpy? How do we ever get that PV term? This is the way you do it. I'm driving it right now. So that PV term would be like a flow work term. That's why they would describe it. The flow is coming into the control volume, and it's the boundary work pushing it into the control volume. Now there's going to be some flow work coming out. It'll be the opposite direction on the outlet pipe. Okay. We already know the conservation of mass equation. Do you know it so well that you could write it by heart? The rate of change of mass in the control volume with respect to time can go up if I have inflow, and can go down if I have outflow or exiting flow. And so if I just show it for one inlet pipe, one outlet pipe, that's a good equation for the conservation of mass. True? Let's pretend we didn't know that equation, and let's derive it using this little illustration here to the side. So what I'm going to do is I'm going to say I'm interested in this being the control volume. It doesn't have to be rectangular, but it's easy to draw it rectangular. So that's our control volume, right? And we want a conservation of mass statement for that control volume. So what we'll do is we'll go back and we'll say, I'm going to consider a system, let me try and draw it with this color, that initially occupies everything in the control volume plus a little bit on the inlet pipe. So that's a control mass which is starting at time t, and the flow is coming in here and going out this other side, and at a later time t plus delta t, it's been perfectly, you pick the time t plus delta t such that all of the fluid which was about ready to enter right here does enter, and then the boundary of the control mass is flush on this surface right here. It comes over, and then you had some fluid flowing out. This may seem like a really kind of weird way to derive an equation that's easy to understand, but let's do it this way, and then we'll do it for the energy balance. We'll do it for a little trickier problem, which is conservation of energy for a control volume. All right, so hopefully I set that up. You have now a control mass at a different time, and it occupies completely the control volume, but now a little bit on the exit pipe. We think about the mass that's about ready to come in and the mass that went out. Okay? The mass that's about ready to come in and the mass that's ready to go out. And then we write a conservation of mass statement for the closed system, which is deforming. It's time t plus delta t. And we say the mass in the closed system, or in the control system, control mass system at time t plus delta t, is equal to the mass in the controlled or closed system at time t. That almost seems too trivial. It's like, yeah, the amount of mass that was there first at time t is equal to the amount of mass at the end. It just was pushed in a little bit on the inlet and pushed out on the exit. Right? Now you employ the trick. You say this part can be busted into two components. It's the mass in the control volume at time t plus delta t, plus the mass that came out, that exited. The combination of this part and that part is the total. You do the same thing over here. You say 2 parts. The mass in the control volume at time t, that's this part, plus the mass that's about ready to flow in, this part. Then you push them, you rearrange them, so you get that mass control volume T plus delta T minus the mass in a control volume at T equal to how much mass came in minus how much mass went out. Somebody guess what I'm going to do next? Divide the whole equation by the time step, the delta T. Take the limit as the delta T goes to 0. So I divide by delta T, delta T, delta T. And you take the limit as delta T goes to 0 of this ratio. And what does that give us? You recall something from math class that said the limit as delta x goes to 0 of f at x plus delta x minus f of x divided by delta x. That limit is equal to, by definition, the derivative df dx. You don't need a whole 4-hour class in Calculus 1. You probably only need half of that for what you get out of it and what you need, or even a third of it. But, I mean, don't leave Cal 1 without what is a derivative, and there it is. That's how you define it mathematically. True? So this whole equation now goes to the rate of change of mass in the control volume with respect to time. So now we're not focused on a quantity of mass, the control mass. We're focusing our analysis on a region of space called a control volume. And in the control volume, you have inlet and outlet flow is equal to the rate of change of mass coming in minus the rate of change, or I would say flow rate of mass exiting. So the mass flow rate in minus the mass flow rate exit. That's what we set out to show, and that's what we've shown, and it's what we started with and we knew already. That may leave you a little cold, right? But now we need to do the same thing for energy. The same thing for energy, because we can write an energy balance equation for a fixed amount of mass for a closed system, and we need it for an open system. And in that process, we're going to come up with H. Oh, that's why we need enthalpy, that new property, that very useful property, which is U plus PV. The internal energy plus the flow work term. Ready to do it? So we already talked about the boundary work. Let's do it for the same system. First of all, just tell me the answer. Give me where do I need to go? My final equation. What does it need to look like? Well, what we would say is we're going to focus on a region in space called a control volume, just like we had for the previous diagram. And we're going to say the rate of change of energy in the control volume with respect to time. It can go up or down. It can go up if I have heat transfer into the control volume. It can go out, so it can go down if I have a work transfer or a power out of the control volume. And notice there's a subscript CV on that W term, because we're going to have not just a shaft work out, but we're going to have to consider boundary work of that control mass as it's being pushed in and pushing out of that control volume. That's why they emphasize CV. It's for the control volume. Think shaft work out of that control volume. All right. We're going to have the mass flow rate coming in. It brings in its internal energy. It brings in its PV. That's the magic. That's a flow work term. It brings in its 1/2 V squared. What's 1/2 V squared? Specific kinetic energy. And it brings in its GZ. What's GZ? Specific gravitational potential energy, or just specific potential energy. And those are all evaluated on the inlet, and I didn't leave enough room. Let me try and scoot this over. I want to put it all on one line. That doesn't look good, does it? Fine, I'll try and squeeze it in. What do you think I need? Minus m dot exit U plus PV plus 1/2 V squared plus GZ, all of that on the exit. It could go out with a different speed, a different elevation, a different internal energy value, a different pressure, a different specific volume. That's right. All those on the exit. So that's our equation. We need to derive this equation. You ready to derive it? That's embedded. That's the reason this PV comes about, well, because of the boundary work term. So what we're going to do is we'll set up and we'll say, this is the closed system at time t. This is the closed system at time t plus delta t. And so we say, let's write down the energy balance equation for a closed system. Okay? So we say, okay, what is it? It's well, actually, let me write it down as in piecemeal, and then I'll turn it into derivatives, just like we did before. We're going to say that the energy in the control mass at time t is going to equal the amount of heat that came in over a time interval by heat transfer minus what went out, think shaft work across the boundary during a time interval. So that's like Q in and work out. And then we're going to have another work. We're going to have these boundary works. I'm going to put it like this. How did I put it before? We did the delta WB, didn't we? All right. Let me emphasize in color. What is this Q dot delta T? That's an in term. What is W dot delta T? It's out. That's why we have a negative on the out. True? That's our sign convention. All right. So let's take a look at WB on the inlet term. All right. From the perspective of the system that's being deformed, the piston is part of the surroundings that's pushing it in. True? So that's work. That's energy transfer by work into the system. That's an in. All right. Let's do the next one. Exit. Why is that exit? Because the system is pushing back the piston as it's going out. So that's an out term. True? Okay, so from our initial amount of energy in the control mass, there could be some gain by heat transfer in, some loss by work transfer out, some gain by the boundary work pushing in, some decrease or out by the boundary work going out. And then you have the very last, energy in the control mass at time t plus, I messed that up. Put this t plus delta t is how much you start with, with the in, with minus the out, and that's what you're left with. All right? Hopefully you followed that. There's a number of ways to write it out, but let's write it out now. All right, what about the energy in the control mass at time t plus delta t? That's going to be the combination of this part and that part. So we'll bust it into the energy in the control volume at t plus delta t plus the energy associated with the mass that went out. Well, what is the energy associated with the mass that went out? U plus 1/2 v squared plus gz, all of that times the amount of mass that exited. Okay, then we're going to have the q dot delta t minus w dot cv delta t plus del w. If you want, we can substitute. What is del w be on the inlet? Pressure, volume, inlet, delta m inlet. True? And then I'm going to run out of room, so I'm going to have to wrap it around. But minus P exit, V exit, delta M exit, then I have to wrap it around. Plus, the energy in the control mass at time t is the energy in the control volume at time t plus U plus 1/2 V squared plus GZ times delta M inlet. And these are all inlets, and that's all exits. So let's group terms. So I'll have energy control volume at T plus delta T minus energy control volume at T equal to Q dot delta T minus W dot CV delta T. Now I need to start grouping terms. So what we'll do is we'll have everything multiplying delta M in. Well, that's going to be U plus PV plus 1/2 V squared plus GZ, all on the in, minus everything multiplying the mass exit, that's U exit, plus pressure exit, specific volume exit, plus 1/2 the velocity exit squared, plus G elevation exit. That's all those terms in there, exit. Let me pause. Did I mess up the math, or are we okay? Next step, divide everything by delta T. Let's cancel. You're back to a rate for the heat transfer, a rate for that shaft work power. And then this becomes the rate of change of energy in the control volume with respect to time equal to Q dot in minus W dot across the control volume boundary out plus the mass flow rate in times. A lot of times we just put enthalpy plus 1/2 V squared plus GZ all on the in minus M dot exit times enthalpy exit plus 1/2 V squared plus GZ exit. There it is. That's what we set out to derive. Is it the same as what we said we were going to derive? The equation's not that hard. I think the derivation's a little tricky because you're going from a control mass to an open system control volume analysis. And the big surprise is why you get enthalpy. And a lot of students say, I think that should be a U only, professor. No, it's U plus PV. Where did that PV come from? From the boundary work associated with pushing fluid into the control volume and having it push its way out of the control volume. You ready to apply it to a number of problems? There's a lot of problems. You just have to take one at a time and apply the principles correctly. What's a nozzle? Well, a nozzle is a device where you have 1D flow, so you have inlet flow here and exit flow here. So a lot of times we'll say it's inlet flow at state 1 and exit flow at state 2. And this is a large cross-sectional area and a small cross-sectional area. So think about the area, compare the areas. Which one's bigger? Is area 1 bigger, equal to, or less? First clicker question, A, B, or C? I'm talking about the inlet area compared to the outlet area as shown for a nozzle. The direction of flow is from left to right. The area 1, is it greater than area 2, or equal to area 2, or less than area 2? All right, so that's what's happening is the area is going down. So area inlet's a lot greater than the area outlet. What about the diameter inlet, diameter outlet? If they're both round outlets, you know, inlet outlet's round, that's common. I don't want to do that again. Which one's larger? Right? All right, what about the pressure? Which way do you think the pressure is going to work? Which one's higher? P1's higher than P2. Why would P2 be higher? Which way is the direction of flow? Which way is the direction of flow from 1 to 2? Right? If I want something to go and it's, okay, how about this one? V, velocity. V1 versus V2. Let's ask a clicker question. It's going to be this way, or this way. Answer A, answer B, or answer C. What does the velocity do? It's a nozzle. What does the velocity do? Well, it does speed up. That's the purpose. So this goes out fast compared to slow input. So the purpose of the nozzle is to boost up. So it's going to come out fast. Isn't this correct? C? Isn't C the correct answer? Yeah, well, I wouldn't say of course. There's 4 people got it wrong, but I asked you. Yeah. So there it is. Now, let me ask this. We introduce a control volume here, and so what we have is across one boundary, inlet, that's state 1 coming in. You have flow, and then state 2 is the outlet going out that way, right? So that's our control volume. Think about how much heat is being transferred. How about Q dot? Let me ask this one. Is Q dot, do you expect it to be less than 0, equal to 0, or greater than 0? What about Q dot, the rate of heat transfer with the surroundings? Q dot for a nozzle. You think it's going to be negative, equal to 0, or positive? Standard model for a nozzle. Do we have enough time? Yeah. All right, so let's take a look at our results for the heat transfer. Well, what's up with the nozzle? What's the purpose of the nozzle? Make things go fast. They come in slow, they go out fast, right? Is it the purpose of a nozzle to transfer heat with the surroundings? That's a heat exchanger. This is not a purpose of a nozzle. So it's a common assumption is we assume that it's 0. Q dot 0. There's no heat transfer with the surroundings. All right, next question, W dot. Do you think the standard assumption is that it'll be negative, or it'll be 0, or it'll be positive? Your answer A, B, or C. What about the W dot now across the control volume? Let me put a CV there. W dot CV. W dot CV for a nozzle. All right, well, is there any shaft that would typically cut across the boundary of the nozzle? I don't, okay. Those are supposed to be softballs and easy. You're supposed to look at the book before you come to class. True. They're not hidden. These are not hidden in the textbook. Okay, these are answers are right available for you. All right, let's do this. For this control volume applied to this nozzle, we're going to do conservation of mass, and we're going to do conservation of energy. All right. For the conservation of mass, that's really, really easy. The rate of change of mass in the control volume with respect to time is equal to the mass flow rate coming in at 1 minus the mass flow rate going out at 2. What about the rate of change of mass in the control volume with respect to time? Positive, negative, 0. 0. Why is it 0? Vast majority of our equipment is running steady state. This is the standard assumption for a nozzle. Almost everything we do is steady state. A very little bit of transient at the end, okay? So this is 0. What's that say about the mass flow rate in compared to the mass flow rate out? They're the same. And so we drop the subscripts. We just talk about the mass flow rate. 5 kilograms per second come in, 5 kilograms per second go out. We're done with the mass, conservation of mass. Let's solve this problem. Steam. Steam at 8 kilograms per second in 80 bar and 520 degrees C and at a speed of 75 meters per second enters a nozzle. And it exits at a given pressure and a given temperature, 60 bar and 500 degrees C. Assuming steady state operation. Even if they didn't say that, that's what you'd have to do. This is, look through the book. It's everything steady state for all these components and a very little bit of transient analysis. Determine the inlet nozzle diameter, then the exit speed of the steam. So maybe I'd go ahead and resketch. Here's a nozzle, state 1, state 2. Maybe I go ahead and list all my properties that are of interest. I'm going to put m.1 as 8 kilograms per second. And then I'm going to talk the mass flow rate coming out at 2. A little bit of work in my mind. They didn't say it was 8 kilograms per second, but we know it's steady state, a little control volume, just like we talked about. And so what comes in at 1 has to go out at 2. So m.2 is 8 kilograms per second. All right. We have the pressure at 1 is 80 bar, and the pressure at 2 is 60 bar. It comes in at high pressure, goes out at low pressure. It's being pushed through the system. Flows like to go from high to low pressure. Nozzles, good example of that. Where it turns around a little bit is a diffuser. We'll talk about a diffuser, but not today. But you can have pressure recovery in a diffuser. How about the temperature at 1? Comes in hot, 520 degrees C. The temperature at 2 is 500 degrees C. It changed temperature a little bit. Does that mean there was a heat transfer with the surroundings because the temperature changed? Don't shake your head yes. No, the standard assumption in the nozzle is Q dot 0. And that's the same as W dot CV. So how did the temperature change if there's no heat transfer? Energy can be in different forms. Enthalpy could change, kinetic energy could change, potential energy could change, but here the potential energy didn't change. Might as well state that. Did they give me any information about the difference between Z1 and Z2? The change in elevation from the inlet to outlet? No. And so the change in elevation is negligible, or you assume it's negligible. All right. How about the inlet speed? 75 meters per second. How about the exit speed? That's what we want to calculate for part 2, don't we? So a lot of times I'll put question mark. That's what I need to calculate. Or I'll put a big underline. That's my answer. That's where I need to put it. I need to calculate the exit speed B2. They have a diameter 1. I don't know the diameter, the inlet diameter. I need to calculate that. Okay, everything is steam. And so I'm thinking, I already applied the conservation of mass to get M2 is equal to 8 kilograms per second. The inlet nozzle diameter, how big it is. You know, that's probably related to the mass flow rate. Because isn't mass flow rate 1, area 1, velocity 1, over the specific volume at 1? Is that equation good? One-dimensional flow? Sure. So, okay, go back over here now. Say, I need to get the specific volume at state 1. I probably, maybe, needed it at 2 as well. Maybe I need the internal energy at 1. Maybe I need the enthalpy at 1. Once you kind of get to the property tables, when in doubt, grab them all for that state. These two, pressure and temperature, fix the state, and we can look up in the steam table and we can get values of V1. What is the value of V1 for this problem? 0.04313 meters cubed per kilogram. And then U1, I'm not going to need it. I don't need U1, but that's my experience telling me I don't need it. But first time you do this, you probably just grab all the values. 3102.7 kilojoules per kilogram, and H1 3447.7 kilojoules per kilogram. All right, so it's like, okay, I just got V1. I have A1. No, I don't know A1. That's my unknown there. But I know M.1, don't I? And I know V1. So what we do is we solve for the area, which is pi d1 squared over 4, which is going to be the mass flow rate, the specific volume at state 1, divided by the velocity at state 1. And so we solve for the area. We find the area is 0.00460 meters squared, and then you solve for the diameter 1, which is area 1, 4 divided by pi square root. And you get D1 is 0.0765 meters. So if you wanted to, you say, oh, about 8 centimeters diameter. All right, so that's the answer to part A. The exit speed of the steam for V2. Well, I've used conservation of mass, probably conservation of energy. So we write down for that control volume, the rate of change of energy in a control volume with respect to time is equal to rate of heat transfer in minus W dot CV out. Then we're going to have plus the mass flow rate coming in times enthalpy plus 1/2 V1 squared plus GZ1 minus the mass flow rate exiting enthalpy 1/2 V2 squared plus GZ2. That's the general form. After a while, I don't like to write it all. I get tired of writing the whole thing down because I know 99% of the time, steady state. For a nozzle, there's no heat, no shaft work. The mass flow rates are the same, they cancel. There's no information about the change in elevation. And what we find is the inlet enthalpy plus the inlet kinetic energy is equal to the exit enthalpy plus the exit specific kinetic energy. Where did that come from? Conservation of energy. So if we're interested in calculating V2, it's going to be V1 squared plus 2 times H1 minus H2 all square rooted. Did I do the algebra okay? All right. I have to scroll down a little bit. Yes, sir. Is that under the radical D1 equals? This is A1 4 over pi. A1 times 4 over pi. Let me scoot down, and I'm going to try and substitute some numbers. So we're going to have 75 squared meters squared per second squared plus 2 times enthalpy 1, 3447.7 minus, oh, I have to go over here and I have to get, I don't need U2, I really need just H2. Yes, and somebody's calling it out for me already, 3422.2 kilojoules per kilogram. So I have to get H2 out of the tables. So I put 3422.2. If I'm the regular student, I close it. I don't worry about units. I just trust the units are going to work out. And I calculate that V2 comes in at 75.3 meters per second. So the nozzle came in at 75 and it came out at 75.3. But I have an error. I'm emphasizing where students often make errors so that fewer of you make the error. I don't want to see this error. Can I say it in a particular way to help you remember? How about if I turn my back to you and I scream, "Don't make this error on an exam"? Some faculty say, I could stand on my head and jump up and down and tell students, "Don't do this," but they'll do it anyway. What's the error? This is kilojoules per kilogram. You have to do a unit conversion. After you do a few of these unit conversions, you know the easy way to write it. But 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. Did I prove that to you already? It's easy to prove, but let's just use it. So we'll do this. I want to get rid of kilojoules per kilogram. So I have to have 1,000 meters squared per second squared. These units go. They combine well with that. And when I take the square root, don't I get meters per second as the final answer? And so this is not right. 75.3, that seemed really low. It came in at 75, went out at 75.3, error. It comes out at around 238 meters per second. I'll be available right after class.